Our next speaker is Elizabeth Taylor. Chris, before you walk too far away, you will please join us at the panel table for the questions later.
A little shorter than he is. Good morning, everybody. As they get the slides up, I am Elizabeth Taylor. I am the project manager for the Automated Reconfigurable Mission Adaptive Digital Assembly System, maybe one of the longest acronyms ever. We refer to it as ARMADAS. And what I'm going to go over today is where we are in developing our technology and our vision to use it on lunar surface. Next slide. So this is a cartoon image from 1982 that shows the concept of using robotics for individual component building. And so it's been a long time that we've been working towards these things, and we're still not quite to that level yet, but we're getting closer. And so there are some great space operations that are going to be coming up, some missions coming up that show this type of technology. OSAM 1 and 2 are an example of that. And we're continuing to develop the concepts along with that to focus on assembly. Next slide. So the big question is, how do you build something this big and complex in space? So we're talking about a moon base, right? We know that something like this requires really high performance and precision for certain aspects of the infrastructure, that you're going to need mission phased approaches to building something this large, that you're going to require mobile assembly and manufacturing agents to be able to do it, because we're not going to have humans there as frequently as we would like, that you need to be able to have components that are repairable and reconfigurable so that we reduce waste and we maximize our reuse of the materials. And we also know that our launch capacity limits what we can get up there. So this increases our need for ISRU usage over time. Next slide. So with the big picture in mind of what we're headed towards, we try to think about what systems can naturally work towards something like this, of this scale. And what we have identified is that your biological systems and your digital systems are really good analogies for this. They're great at combining building blocks and creating hierarchical structures. And with that, you can see that these give us really scalable designs, that you have something that is repeatable and exact, and you've got a small set of parts that you use to create that. So next slide. So understanding that, we have evaluated and looked at the different capabilities and come up with discrete mechanical metamaterials as our building block for assembly. And so what these assembly approaches give us the ability to do is have something that's reconfigurable. It makes it much easier to scale and to tune your structure to your specific needs. And it provides something that can be ultralight and repairable. So you can see on your left an example of how the team reused the individual components here. This was done in Yosemite. They took those individual components in 2 backpacks, unpacked them, and made a boat, a habitat, and a bridge. And so they demonstrated early on the capability to do that reconfiguration. Prior to that, they also did some work on an arrow wing. So they took different shapes for your kit, essentially, and constructed a full-scale wing that was tested in a wind tunnel and showed that it could dynamically tune itself using the structure itself. And then, of course, the ultralight and repairable, being modular and component-based, gives you that capability. Next slide. So a lot of that work was done by hand, the assembly of those components. And so we know that for going to lunar surface and for going into space, we need to use robotics and autonomy to assemble these systems. With that, we also understand that those digital discrete mechanical metamaterials provide a really discrete environment, which makes our robotics and our autonomous problem a lot simpler to solve. So our global precision that you see comes from parts. So just like Legos, Lego bricks are precise down to the micron for the individual components as you put them together. The assemblers, however, are not very precise. So they are relying on the part itself to create the precision that's necessary to create the structure that they're trying to build. And our robots are similar in that concept. So that also allows us to have a lot of reliability and error detection capability. Our assemblers can then become much smaller than our structure because they can crawl around it and build something much larger than they are. And it also provides some energy efficiency with our mechanical connections, not having to use heat fusion, things like that. Next slide. So overall, our technology integrates three key components. Our structures, of course, the robotics that traverse along the structure itself and help place and build the components, and our autonomy that does our path planning and trajectories and actual design of how the structure will come together. Next slide. So this is where we actually are. I'm not going to go into a lot of detail on this because I hope you guys understand we are in the process of developing publications and getting them out, which hopefully you will see soon. But we did just complete a ground demonstration that autonomously assembled 256 components. And it was a great success. Everything worked beautifully, and we're excited to share the findings and data that we get out of that. Next slide. So overall, the demonstration did show that we can use those lightweight materials, that they bypass the performance of our typical production methods, that they give us a really precise and scalable infrastructure, and that autonomous assembly and reconfiguration is possible using these discrete algorithms and our task-specific robots. So we have, I didn't mention this, but we have 3 robots that were a part of that assembly, 2 that traverse along the top, and 1 that crawls inside the structure itself to do the bolting of the pieces. And finally, it gives us an integrated system that enables this large-scale type of infrastructure that we hope to accomplish. Next slide. So given where we are, we want to share with you our vision for how this will look on lunar surface. Next slide. So I'll go back to the Lego analogy. You can see here, and I'm sure you guys are familiar with the fact that Lego puts together kits, and they provide you the different piece parts that you need to develop whatever it is you're looking to accomplish. And so like Lego, we have our own question of what are our building blocks supposed to be? What does our construction kit look like? And what do we need to do to be able to make that a reality? And the other piece that goes along with this, of course, is that once you're done with that kit, with that infrastructure, you can take it back apart and use the pieces for something else. Next slide. So this is what we envision as a lunar construction kit. So you've got your basic structural voxel or unit cell. You could have a solar panel attached to one. You could have a rail voxel attached to a piece. You could have one that is metallicized and used for power and comm routing. We have a structural panel, and then we have a footer voxel that helps us with our stability. Next slide. So taking these kit of parts, you can imagine that using them in combined ways will give us a lot of applicability for general purposes. So you could have your lunar towers, you can have your berms, you can have your shelters and railways. There's a lot of opportunity, a lot of broad applicability for this type of technology. Next slide. So to give you some ideas of what those combinations might look like, if you use the solar voxel and a power comm routing voxel, perhaps you could create a robot charging station. Combine those with a rail voxel, and you could get yourself a self-powered rail system. And then, of course, with the panels themselves, you could have a wall or a shelter or a blast berm, those types of things. Next slide. So we've also talked about towers, and so I wanted to focus more on the footing piece here. The bottom there is supposed to show you how variable the terrain can be to manage leveling to get the structure that you need without having to do site preparation necessarily. So this is our adaptive footing. Next slide. So along with that adaptive footing, we recognize that you won't need feet at every spot on the ground. So you can, of course, intersperse your regular voxels within that. And then secondarily, if you need additional reinforcement, you can use Regolith, loosely piled or otherwise, around the footers to help create additional strength. Next slide. When it comes to the rail station, we think that this is a great way to reduce energy for transport between commonly accessed locations. So you have your areas that you know are going to be dirty, that you're going to lift up dust and create a more dirty environment. And then you're going to have areas where you want it to be more clean and you don't want to be stirring things up. And so being able to transport things without stirring up the dust could be really valuable. And so what we've looked at and theorized on is that you could have a track that has solar panels that helps it run, and then the carts on top of it could have a sweeping system that help clean the solar panels as they go. Next slide. So integration with our Regolith, of course, is something that we are interested in, and we talked about having that as helping reinforce the structural foundation, but we've also looked at it as a potential for helping mitigate radiation. So we know that there's interest in using that. There are multiple ways that we could go about this. So the first concept would just be loosely piling it on top of the structure. The other concepts involve more along the lines of filling the inside of these voxels and walls to create a more structured wall system that you might be looking for. And then the last one is more along the lines of each of those individual voxels having some hardened regolith within them that could then be placed individually. Next slide. So ISRU integration, of course, is something that we hope to take advantage of over time. It's not necessary for us to get started, but it is something that is possible for us to integrate over time. So we basically are manufacturing agnostic. We can use a small set of parts that we fly. We can be 3D printed, or we can be casted, which would be wonderful. Next slide. And then for the last part here, I think this is the last one, is our customized outfitting and user integration. And this is some new ideas that we're kind of excited about. The idea of sharing the voxel space essentially and allowing users to determine what they want to put inside of it. So imagine creating your own voxel that then we can help assemble into the infrastructure. Or having ways to attach your structure, your system to the outside of that structure. So our internal locomotion robots that I mentioned as well also help with outfitting as far as being able to release cabling and helping with that type of outfitting. So you can see it in the tower. He's crawling up the middle of it and he's got a spool that's releasing the wire. Next slide. So a large part of the concepts here are really designed to help enable the cost scaling curve for what we're trying to do on lunar surfaces. Because once you have that individual voxel shape that can be reused over and over, and you have the similar robots that you can have multiple of to expedite your construction, the cost as you produce more of those goes down. So that is something that we think is really value added as well. Next slide. So in summary, this just gives you an overview of everything I just talked about related to the system of what we're looking at. You've got our scalable and reconfigurable design opportunities, our reconfigurable building blocks and repairable lightweight materials that we can take advantage of ISRU for, our structures that bypass performance, and then these small cooperative robots that help do the assembly and leverage that discrete environment. And finally, one I didn't really hit on, but digital twin for planning, verification, and validation. So you can see we've got some simulation happening right there that shows multiple disparate locations where the robots are grabbing their voxels from and building the structure. And then across the bottom is really some of the applications that we see this being valuable for. And of course, another picture of the construction kit and where we hope to go. And I think that's it. Thank you guys so much.